Hello everyone. I hope I am audible. Okay, so we will be discussing about the yesterday's AtCoder contest. How many of you have given the contest? Okay, so how many questions were you able to solve during the contest?
I was able to solve three, but on the third one, in some cases, TLE was there.
Okay, the third one, right? Reverse permutation problem.
Yes.
Yeah, it was a bit of observation over here. We will discuss that shortly. So let us start the PCD. I hope my screen is visible. Yes. So let me start the proceeding for it. We will be starting off with the problem A, supermajority. The problem intuitively says you are given two positive integers A and B. If A greater than B into 2 by 3, output yes, otherwise output no. The problem is quite straightforward. Just need to check this condition and then you just need to print yes or no. So this was quite easy. We can move on to the next problem. So, parking too. Basically, the problem says there's a parking lot. The fee for the parking for this lot is as follows. During the period from exactly L to exactly R o'clock, a fee of X is charged for each hour parked. During the period not covered above, a fee of Y is charged for each hour parked. Basically, let me go to the board. In the problem, there is given a range A to B, right? Uh, like you are parking a car from A to B range, A to B, and there is a range given L to R in it. Suppose this is the L, this is the R, and the problem says uh, between this L to R, for each hour parked between this L to R, the problem is charging us, I think X amount of points, right? And for these extra hours, like from L to A or A to L basically, and R to B, it is charging us Y coins, right? Extra. So we just need to like add these extra contributions, this contribution. So this is what the code must be, right? Nothing fancy in itself. So uh, let us move on to the next problem. I hope it is clear till now. So the constraints are also quite less. You just need to check the ranges. So it would be a lot easier. Uh, Move on to the next problem. So the third problem, reverse permutation. You are given an integer n and a string s of length n consisting of o and x, right? There is an integer sequence a of length n. Initially, a is given. Uh, Perform the following operation on a for k is equals to 1 से लेके n तक in this order. If s of k is 0, reverse the first k terms of a, right? So we reverse this part of the string of the or the array. And if s of k is x, we do nothing. So we need to print the final array after all the operations, right? So one thing to observe over here. Okay, let me take up the code again. Arnav, what was the logic you were looking for in this problem?
I was simply going with the brute force that if it is X, then I ran a for loop till the n elements, and if O is there, then a for loop to exchange the elements from j is equal to 0 to j less than I by 2. So each elements get exchanged till that. And
But you know the constraints, right?
yes,
So that
After
wouldn't
setting
pass.
additional constraints, that's why.
So you need to look for an optimal, right? Uh, can you look for an observation over here? If you look for this test case, okay, let me discuss it. We were given with a test case O O X O O, right? The initial array is 1, 2, 3, 4, 5. What I can say about here is, if the last index has a O, that means we have we have reversed the entire array, right? If we have reversed the entire array, there was a 5 over here, so that 5 would go here now. So when forming the final array, we can put a 5 over here. Now we can look for uh, the second last element, right? We can go for this element now. If we look for this element, there's again we have reversed the array, right? Up to this element, up to this index, we have reversed the array again. So we have reversed twice, right? So if we were only reversed this part, right? If we had only reversed once in this index, so our 4 must have been over here. But we reversed it again, right? So our 4 would have gone over here. Like we reversed this part, right? Uh, let me take it up. If we reverse it at the last index, our array would have become something like this: 5, 4, 3, 2, 1, right? So if we reversed again at this index, the last index, the second last index basically. So like we are reversing this part of the array, right? The first 4 elements would now mean the last 4 elements, right? In the reverse manner. So we reverse this part of the array. So this 4 eventually goes up over here, right? So the final array after this operation would become something like this: 5, 1, 2, 3, and a 4 over here. So you notice the difference, right? If we reverse two times, we originally push the element towards the right side, right? If we reverse it like an odd number of times, we push it in the front side, right? Let me take up again for the next indexes. Change the color. If we look for this index, this is a cross, so we do nothing over here. So we move on to the next index. Uh, this has a like we basically reverse this part of the array, right? Basically reverse the first two elements of the array. So the the first two elements of the array would be like this, right? Uh, so the first two elements of the array would be like this, right? So we reverse this part of the array. Oh, the this would be like this, right? Because we have reversed an odd number of times over here. So this would become something like this in the reverse manner. So this would lead us to an effective array of so this would be our net array, right? So if we reverse it again over this index, right? If we reverse it over here at this index, so we are basically reversing this part of the array. If you can get it, we are basically reversing this part of the array. After reversing this part of the array would become something like this. which is the final answer, right? Basically, what you need to think about is we are fixing the elements. Like 4 was reversed over here twice, right? So 4, uh, like 4 would have come over here initially, and then 4 would have reached over here if we reverse it twice. So we have fixed 4, we have fixed 5, and then we look on to reverse the next two elements, right? So the next two elements would go from here, right? So this is what we need to look for. Arnav, is it clear?
I guess in the final answer, the position of 3 and 2 are swapped in your answer. That would be correct.
Okay. Uh, the final array, right?
Yes.
Okay. I think I swapped it. I think this should have been it, right? Uh, yes, I think this should have been in the final, right? Exchange.
Yeah.
So yes, that is what the complete intuition was basically. You need to reverse some part of the array such that uh, like we are basically fixing each element, right? After each reverses, you need to check whether the position of the element in the final array, right? Like if we're reversing an element twice, we know which position we should look for. So this is what the complete intuition for this problem was. So
Yes.
what we can do to implement this is uh, we can take up two indexes. Like uh, this is the array we need to form. We can take up two indexes over here and one over here at the last. Suppose we are like we iterate from the end of the string. If we encounter a O, we basically store it in our count. We count the number of O's encountered till now, or basically we perform the reverses. So we store the number of O in the count. If we have performed the reverse operation odd number of times, like we have performed the reverse operation odd number of times, we push the element this side, right? Because if we have performed the reverse operation even number of times, this would cancel out, right? Even number of times reverses, or like we reverse an entire array twice, so that would mean nothing. So we enter the element over here, we push the element over here. Let's say we are looking for 5. So we put the 5 over here and we move this pointer to over here. And now, like in the string we were given as O, O, X. So we are done for this index. Now we move on to this index. So the number of O's encountered till now is 2. So we push it for this side if it is even. So we push a 4 over here and we move on to this index. So we move on to this index then. The number of O's encountered is still even. So we push a 3 over here. Now we move on to this index again. So we move on to this index. The O's encountered over here is odd, right? So we push a 2 over here at this index. And then we move this over here pointer. And similarly like this, the O's encountered over here are even. So we put up 1 over here. So this is what the problem uh, asks us to do. So it was a two pointer concept basically. Let me take up to the code. Uh, like I said, there would be two indexes we need to monitor. One is the at the start of the array, and one is at the end of the array. And I've taken a flag or basically the mod value of the count of the O's encountered, right, or the tasks performed reverses, basically. The flag 0 means we have performed nothing till now. If we encounter a reverse operation, I am basically setting it to 1. Like we have performed odd number of operations, right? So if odd number of operations are performed, we enter the element at the start, and then we move the index ahead. And if we have performed an even number of operations, we enter the element at the end of the array, and then we move ahead the pointer. So we now print the final answer. This is what the code would have something with. I hope is it clear. So we move on to the next problem. Dx to y. What the problem says, we are given two integers x and y and an integer k that is at least 2. There is a variable x which is initially x is equals to capital X. You can perform the following operation on x more or 0 or more times, right? Choose an integer y satisfying x by k, the GIF is y, or y by k GIF is x, and replace the value of x with y. What this statement basically means is, uh, I take up the code. Since suppose we are given x by k, GIF is equals to y. So, like we can convert it. Uh, like the. I hope you everyone over here knows the working of this, right? This GIF function. Suppose we have a decimal value over here. We take a number, arbitrary number, 3.14. So this would return me 3. So we truncate the decimal places over here and return the integer itself. So this is what the function does. And now we try to reduce this statement into something meaningful. Uh, the question where in the question we were given two things, right? Uh, okay, in the question we are given two things. X by k GIF can be converted to y, and y by k GIF can be assigned to x. So this intuitively means uh, x by k GIF is y. So y can be intuitively represented as x by k, right? Because in division format, we also like truncate the decimal places, right? Suppose if x is 7 and k is 2, so 7 by 2 in CPP gives me 3, right? If we do it in long format or integer format. So we can reduce this part to simply this. Uh, so the next expression was something like this. Uh, the next expression was something like y by k gives me x. And we need to convert it with respect to y because we are changing x to y. So we need to look for the variable y. What this means is uh, y is something greater than x into k. Y is something greater than x into k. X into k plus r. This r can vary between 0 to k minus 1. Right. Let me take up an example. Uh, say it is, let's say uh, our y is uh, 21 maybe, and our k is 4. Let's say so. 21 by 4 should give me 5, right? The greatest integer part of it should give me 5. So, like you can say it 21 is 1 more than 4 into 5, right? So this is what comes over here. Uh, we can basically break it down to 21 plus something r by k. Uh, so like this would give me 5, right? So this is what the condition was basically. So we have converted these two statements into these two equations, right? Uh, this is a valid equation. This is a equation. Now let me discuss what we were asked in the problem clearly. Uh, we were given two integers in the problem, x and y. We need to convert x to y somehow. Uh, we can perform these operations in the during the conversion, right? We can perform these operations. Let's say we were assigning a number x initially, small x to x, and then we perform, and then we can like we can perform operations on this number x and convert it to y, and then we need to convert it to capital Y in the finally, right? So we need to report the number of operations, the minimum number of operations we can do it, in which we can do it, right? So let me take up an example from the problem itself. We were given t test cases. T was varying up till 10 to 5, and x and y are also varying up to 10 to 18. K is also 10 to 18. Okay. Let me take up this test case. 11, 9, and 3. So x is 11, y is 9, and k is 3. So we need to convert 11 to 9 somehow using these operations. Let's discuss how we can do it. We can, like 11 is still greater than 9, right? So we cannot multiply it to make it smaller, right? Multiplying it to make it smaller would mean no sense. So we need to divide it by 3, right? Like the operations we can perform over here we discussed, right? The new number can be the older number greater by k, or the newer number can be multiplied by k plus something remainder. So we cannot multiply it over here to make it smaller, so we need to divide it over here. So we divided by k, right? K is 3 over here. We divided by 3. 11 by 3 gives me 3, right? uh, and now the new number is smaller, right? Now we check with it. If like this is the x now, this is the updated x now. The initially x was 11, so this is the updated x now, and then we look for a y, right? Uh, if we check, like we can multiply it to get this 9. Y was like we can divide it by 3. If we divide this number by 3, we would get a 1, right? So this makes no sense. What if we can multiply it over here? So the updated y would be like something like it would not be a specific number. It would vary from a range, right? I think you can get it. It would be varying within a range. Like this number x into k. So 3 into 3 plus something r. R was between 0 to k minus 1. Here k minus 1 would be like 2, right? So it can either be 0, it can either be 1 or a 2. So these are the set of values R can take over here. So our number y can be a number within this range, right? So it would be like 9 plus 0. So the minimum value would be 9, and the maximum value would be 9 plus 2, 11, right? So our new y is within this range. So basically we need to check all the values of y possible, and like we need to check if this capital Y lies in this range, right? The capital Y lies in this range, as we can see. So our final answer, we get a final answer, right? We need a one operation to divide it, and then we need a one operation to create this range using multiplication, right? So it would take us two operations basically. So this is what the uh, initial test case was. This test case does not seems to be harder, right? X and Y are obviously the same over here only, so we'll not need to perform any operation to make them same. Uh, Let us take on this test case again, 84218T, right? In case 7. So uh, then we can discuss the intuition behind it. X was given as 842, right? 842. Y was given as 180, I guess. K was given as 7. So we need to check if we like in the question it is guaranteed, right? We can obviously convert all X to all Y. So we need to check. We need to like report the number of minimum operations we can do to perform X to Y. So uh, what we can do is X is greater than Y initially. So we can divide it over here. Multiplying would mean no sense. So like we divide it over here. 842 divided by K would give me 120. 840 by 7 is 120, right? And then 120 is like slightly lesser than 180, not much lesser. Like if we can multiply it, there are no conditions for it, right? Like if you can think of it, 120, like if I multiply it over here, like there can be two operations, right? Like a binary tree in itself. So if we choose the multiplication operation, uh, multiplied by 7 or the k basically, and some plus some remainder. So 120 into 7 would give me 840. So I hope you see, like if we perform the multiplication and division like very intuitive, like very simultaneously, so this would mean no sense, right? So 840 plus some remainder. So that did not convert our number, right? If we divide it by 7 again, we would be like directed to this number, right? 120 again. Like if I divide it by 7, so I would get the 120 back, right? So we do not perform this operation now. We do not perform this. So we need to check if we can perform this division. So we go for this division, right? 120 divided by 7 would be 17, right? So this would be 17. What if we can divide it again? Or like if we can check if we can multiply it or not. Uh, so there are two cases. If we can multiply it by 7, so 17 into 7 would give me, I guess, 119, 119 plus some remainder. That remainder can be between 0 to 6. So this is what multiplication by 7 would give me. Uh, so we can divide it by 7 again if we wish. So division by 7 would give me 17 divided by 7 would give me 2. And if we perform the division again, we can get a 0, right? So the observation to look over here was this. We can convert any number to a 0, like 17, not 17 basically. We started off with 842, right? So like we can convert any number to a 0. Like this can be traced back to 842 and we reached a 0 over here, right, by division. So we can like convert any number to 0, right? If we can convert any number to 0, we can then start multiplying and then with the help of remainders, we can convert any 0 to this y, right? Let me take up an example. Uh, so the number of operations required uh, took by us to convert this number to 0 was like this took one operation, this again took one operation, this again took one operation, this again took one operation. So there was four operations required in this, right? So if we convert a 0 to maybe something into 7 plus remainder, so the range would be like, I hope you understand, it would be from 0 to 6, right? This 0 can be converted to a range with multiplication to 0 to 6. Uh, like 0 into 7 would give me a 0, and then we add the remainder. So the range over here would a 6. And then we again perform the multiplication operation. So 0 into 7 would be 0 plus the remainder. I am adding the remainder. Then 6 into 7, 42 plus the remainder. Now, as we are forming a range, we need to look for the minimum and maximum values, right, of this. So the minimum value for this range can be when r is 0, the remainder taken over here is 0, right? So we take a 0 over here. Uh, and for this, when the r is 6, right? So 42 plus 6 gives me 48. So 0 to 48. Uh, then like as the number, like as the maximum number in this range is still lesser than this y, right? We needed to convert it to 140. So the range is still smaller than this number, right? So we again perform the multiplication operation. Uh, so we multiply it by 7 and then add the remainder, right? So 0 into 7 would still give me 0 plus the remainder. And then 48 into 7 would give me uh, 336, right? 336 plus remainder. Okay. Now, the maximum and minimum value for this range would turn out to be when r is 0 for this. So this would be a 0. And when we put a 6 over here, right? So this would turn out to be 342. So we can see, right, our y, uh, our capital Y in the question was given to be 180, right? So basically, we can convert any number from 0 till 342 in this set of operations, right? So our y is in this range, lies. Our y lies in this range, right? So it means that y can also be converted with the number of set operations, right? Uh, for like y, we can take some r in between, and then we can reach up to y. So this is what the problem like basically means. Uh, I hope it is clear. I don't know.
Yes, big.
So now we look for the optimal approach to do this during the contest, right? So uh, let me change the. I hope you get. We can like divide x and get the number and their operations required for it, right? We can divide it and get the number of operations required to convert that number from 842, right? So what if we can do that for y itself? Like instead of looking for the remainder, we need to add over here. We like do like we divide the y and then look for the number of operations like numbers we can form over here from y. Let me take. So our x given was 842. So we can divide over here to get 120. We can again divide over here to get a 17. We can again divide it over here to get a 2. and then we can divide it over here to get a 0, right? So what we are saying is, instead of multiplying it back, what we can do is we can divide the final number, right? Like we need to convert a 180, right? So what if we can divide the final number in itself? 180 divided by 7 would be 25, right? So we need to convert it to again division, right? Perform the division again. So this would give me 3, and then 3 divided by 7 would give me a 0, right? So we divided the final number. We need to perform, right? So we can like reach the like we can observe, right, the meeting point between these two pathways. Like this is a pathway and this is a pathway. Like the first meeting point in this pathway was at 0, right? So what if we can do it something like this? Uh, let's say we go on dividing the number x, and then we go on dividing the number y. Uh, what if we collide in between, and then like if we collide in between that, like this would come out to be straight path, right? Like this would be a merged part, a common part for both of them, right? uh, like if this number is same, so the division by 7 would be this number, right? So this would also be the same. So you can look for like this would be a common part for both of them. So we need to check whether like the point where they actually merge between. And then if we can go like dividing on, and then like if we can go on dividing x up to this point, and then if we can go on multiplying up to reach y, right? Let me take up an different example if possible. Uh, okay, we can take up this example, right? 11, 9, and 3. 11, we go on dividing 11. This would give me 3. We go on dividing it again. This would give me a 1. We divide it again. This would give me a 0. Uh, now we divide 9. So this would give me a 3. We divide it again. This would give me a 1. We divide it again. This would give me a 0, right? So you can observe the path. Uh, there's a lot of common in itself. This part is actually common, right? So let me like do we like does it make some sense if we go on dividing uh, beyond this point? If we go on dividing beyond this point, like if I perform the operation, this should be an operation. Like if we perform this operation uh, while dividing x, and then we need to return it back, right? So we do not need to take the longer path, right, to go up to this number. So what we say is we go up to the first merging point where they actually merge, and then like if we can go on multiplication to get the final number y. So this was our optimal approach. Uh, Let me also discuss why first we need to perform division and then we need to perform multiplication. What if like there was a sort of like random manner of division and multiplication in between? Okay, like you can also observe it using some maths. Like if we have a number x, we need like if we perform a multiplication over here with k, and then a division with the next operation. So this would cancel out, right? Basically, so we like wasted our two operations. So this would not fetch us the minimum number of operations, right? So what we can do is we can either perform first division and then go on to perform multiplication with the remainder thing. So this would give me like the minimum number of operations, right? Because we like if we perform the multiplication anyhow in the beginning, so this would waste our operations, right? Like if we perform some set of multiplication uh, and then we perform division operations, so like these two division operations would cancel out these two multiplication operations, right? So we like order this in this manner: first division, then multiplication. Perform all the divisions in the beginning, you need to perform and then all the multiplications at the end. So, like you can solve it in two manners for this problem. Either you can go up to for this range thing, uh, like you can calculate the range. You can reach up to using multiplication from the like at any point in the number. So you can go for this thing, or you can go for this thing, dividing both x and y. We get up to the first merging point, and then we go on to multiply it back, right? So this is what our problem would be. Uh, Now, how do we go on to implement this solution? Okay, let's say we start on dividing the x first. So we start on dividing the x first. X was 11. What we say is the number of operations required for like for x we are doing it, right? So the number of operations required to convert 11 from 11 is 0, right? Uh, and then we move on to this part 3. What we say is the number of operations required to convert 3 from 11 is 1. The number of operations required to convert 1 from 11 is 2 because we perform two divisions. The number of operations required to perform 0 from 11 is 3, right? Uh, then we go on to divide it 9, right? So the number of operations required from 9 to reach 9 is 0. The number of operations required to reach 3 from 9 is 1. And then we can check if the number of operations like x also has a common point in this or not. If there is a common point, we can simply add both the number of operations and then return this. Like 1 plus 1 would give me a 2. We return this part. So this is what our like optimal approach would be. I hope it is clear. Arnav.
Yes, Bhaiya.
So this is how we implement it. If we take up to the implementation So we take the input over here, x, y, and k. We take up a map and like store the distance. Basically, distance would mean over here the number of operations required for it to convert. So we currently have a x. We are currently at x. We need to divide x, right? The steps for it is 0 to get x from x. So if x is greater than 0, like so we divide it over here and then store the count for it, right? The number of operations required to convert this number divided by k. So we do it for y again, and then we check if we have a y over here in the map previously stored or not. Like if we encountered a middle point or not, or the common part between them. Like if we are at the common part, we return the number of operations required to get this number from x plus this y, right? From the k, from the y basically. Steps we're storing the number of operations required to get this number from y. So we get uh, these two and we add them and return simply. Otherwise, we keep on storing them. So this would be it. Uh, so the problem D would be this much. Uh, then we go on to the problem E. Uh, so Arnav, were you able to think of this problem or anyone, I guess, for the problem E? Like the problem E states some conditions, right? We need to count the number of integers x we can get such that x lies between 1 to n, and it satisfies exactly one of these three conditions. Either x is a multiple of 3, or either the decimal representation of x contains 3, or there are exactly three different digits used in the decimal representation of x. So we can like look at the constraints over here. The n, like the upper cap was given up to 10 is to 500, right? This pretty much sounds horrifying in itself. So, like, if we convert it to string, if we convert the number to string, like you can look up to this. Uh, Suppose I am given the number 10 is for 3, which is basically 1000. So, if we convert this number to string, or which is basically this, so the number of places for it is 4, right? Required to store this number is 4. So 3 plus 1 is 4. So like you can convert the number to string basically. So uh, so if 10 is for 500, like such a big number would be converted to string. So this would be up to 500 places, right? 501 places exactly. So uh, so for this problem, n can be converted to string, uh, and then we need to count the number of integers x possible, right? So like there can be an overlap in between these two conditions, right? And multiple conditions there can be overlap in between these three conditions. Like x is a multiple of 3, at the same time x can have a 3 in the decimal representation of it, right? So like this is sort of inclusion exclusion problem, right? Like we include this condition first, then we include this, then we include this condition, then we look for the common part between these two conditions, then we look for the common part between these two conditions and subtract them, uh, the first and the third. Then we look for the common part between these three conditions, the final overlap, and then we add it. So, like the problem does not sounds good for an inclusion exclusion problem over here. The conditions are too much heavy. Like this problem can be solved using digit DP idea a bit. Like you can maintain some states in the DP uh, to solve this problem. I can discuss the idea which you can use. I have not yet implemented it myself right now, so let me take up the idea. So we are given with 501 places, right? 501 places of the number. So we need to like form a number of uh, like number of places 0. Like it can be a place. No, like it cannot be a place of 0, right? They are given to form the number between 1 and the n, right? So a 0 cannot be there. So it can be of 1, 2, two digit of like 500 digits up to, or basically the number of digits in the n, right? So what we can do is we can maintain a state. Uh, like if we convert the number to index, if we convert n to string, if we convert this n to string, suppose the n was like for 5 places I'm considering 3, 4, 5, 2, 1. So let's say our n was initially this. We convert this to string, and then we go on for this part. We look for to form the number in this part, or the digits we can place in this part of the number. So the states we need to look for is an index first. The state would look we need to look for is the index we are currently at. Let's say we are at this index and we are looking for the digits we can put up over here. So the first would be the index we are at, and then uh, the next state might be if we have a leading zeros over here. Uh, like what do I mean by this actually is Suppose our number we have formed up to this two zeros, and we are at this index. We are deciding for this index the number of digits we can place over here. If we have a leading zeros, like the question briefly states, we cannot like include the number with leading zeros, right? We cannot include the leading zeros in the number itself. So like leading zeros जो हम लोग स्टोर करेंगे वो आगे भी काम आएगा. Like if we reach up to the end of the number, if we reach up to the end of the number, we are sure we have formed a number specifically. And if the leading zeros at this point also is true, right? Like if we have filled all the number with zeros in itself, so this is not a valid configuration, right, for our number because we need to form it between 1 and n, right? So this would help us. So we go back. Okay. Now we look for this, right? So our second state can be leading zeros, LZ in short. Uh, then our next state can be if the number is tight or not. Uh, what do I mean by tight? Let me discuss it. Suppose. Suppose we have put up a 3 over here at this point, a 4 over here at this point, and we are looking to place the digits over here, right? Like we can place a 0 over here, a 1 over here, a 2 over here as well, and 3 up to 5 we can place it, right? We cannot go beyond 5, right? Like if we try to place a 6 over here, you can understand like this would exceed the condition we are stated in the question, right? The number can be equal to 1 to n, right? So this would exceed the condition we are stated in the question. So 3 4 uh, 3 4 6, and then the last two digits can be anything like. So this number would be an invalid number, right, for our case. So is tight helps us to check whether the number is currently tight or not, or basically we are forming the a valid number or not, basically. So we need to store is tight as well, and then like we can store uh, one condition for each of the three conditions. Like we can store one state for each of the three conditions. We can store a digit sum. Uh, like it would store the sum of the digits we have formed till now. This would help in identifying the multiple of three. For a multiple of three, we know the condition, right? The total digit sum of the number should be a multiple of three as well. So this would help in this. The decimal representation of x contains three. So we can store up a boolean value in itself if we wish to. Uh, like if we have like if we have stored a 3 over here, so it would give me a true. Like if we have stored a 3, or if we have not stored a 3 up till the end, it would give me a false. So uh, maintaining this state was easy. uh, so the next state was exactly three different digits are used in the decimal representation of x. So what we can do for this is uh, we can take a state up to 5. Like uh, like we can handle a set over here, basically set. We can handle a set over here to store the number of unique digits in it up till this point, and then we can store the count of it. So like the core idea of the problem was this. Implementation is on your side. uh, so I hope this approach was clear enough. So that's it for the PCD today. uh, if you have any doubts, you're free to ask, or else you can leave the meet.